Okay, so I've put a bunch of data on this page. And what it is, they're power tables. So these are mods right here. This is mod 11, mod 13, mod 15. Further down is mod 17, mod 22. If you look at what's going on here, I take a column like 2, and I want to think about the powers of 2 mod 11. So, right, so like 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, which is 5 mod 11, and so on. In fact, you would just multiply by 2 and then reduce mod 11 each time to get the next entry in each column, right? So the column headings are the elements of U sub m, they're the units mod m, right? So like in the 15 table, these are just the numbers that are relatively prime to 15. So we don't have 3, we don't have 5, because we don't have 10. We don't have any numbers that share common factors with 15. And then the entry, so then I guess the entry in column A, row n, is a to the n mod m. Right? Okay. And, you know, as we look at these, some patterns start to jump out immediately. That there's rows of all ones. That, you know, even for 17, there's a row of all ones right there. For 22, there's a row of ones right there. And for the prime mods, for 11, 13, and 17, it's pretty jumps out. It jumps out at you that for 11, the 10th row is the one where you get all ones. For 13, the 12th row is the one where you get all ones. For 17, the 16th row is where you get all ones. And that leads to what's called Formosal Theorem, which is basically says that, let me state it. So Formosal Theorem it says that given P prime and A relatively prime to P, which you could also just state as P doesn't divide A, right? The only things not relatively prime to primes are multiples of their primes. If we have this setup, then A to the P minus 1 power is congruent to 1 mod P. So that jumps out at us in the table that, you know, everything to the 16th power in this table, everything to the 16th power is 1 mod 17, and so on. But what about the non-prime mods like 15 and 22 here? Well, another way to say 16, like another reason 16 is here, is there's actually 16 columns of this table, right? And 10, there's actually 10 columns here. There's 10 elements in U sub n, m, and in U sub 11, right? So to generalize, if we want to talk about non-prime mods, let U sub m, well, let like this, maybe for a set S, let this represent the number of elements of S. then for given A and U sub M, A to the number of things in U sub M is 1 mod M. Right? That seems to be the generalization. Right? U sub P, by the way, has P minus 1 elements in it. And so that gives us this. I can say something even a little bit more. There's actually a name. There's actually a name for the size of U sub M, right? We've seen that U sub M, the units mod M, is the set of numbers relatively prime. Numbers relatively prime to M and less than M. That was a very, I could write it better probably as it's the set of numbers, I guess, well, maybe I should say 0. Set of numbers between 0 and M strictly, such that A and M are relatively prime. And so that means that this this number really counts the number of numbers. How many numbers, how many positive integers are less than M and relatively prime to M? Less than M and relatively prime to M. And this actually has a more famous name. It's called the Euler Fee function. Euler Fee function, phi of M. So that's really the size of U sub M. And again, phi of P for P prime is P minus 1, right? Because everything between 0 and P is relatively prime to P. Okay, so the generalized, I can restate this. This was kind of the generalized Fermat's little theorem, but the way you'll really see it stated is, let me just write it out, and then I'm going to prove it. It says, right, given A and U sub M, so a unit mod M, A to the phi of M is, I could say equals 1 in U sub M, or I could say it's congruent to 1 mod M. Okay, so how can we prove this? And Formosal theorem, again, is a specific case. When M is prime, we recover Formosal theorem. Why is this true? It's the real question I want to ask. So there's a nice argument. Let's look back up at this table. Let's say the 15 table. By the way, so I will say it's worth mentioning here that I do recognize that the fourth power of everything is also 1. We'll talk about that later, but what Formosal theorem says, or the generalization says, is that in this case, that the 8th power of everything is 1 because there's 8 columns here. There's 8 elements. There's 8 numbers relatively prime to 15 and less than 15. Okay, so so let's just say I wanted to prove this for a specific example. Yeah, so let's say like I wanted to show that yeah, let's just say 7. I wanted to show that 7 to the 8th power is 1 in U15. So this might be a little bit of a proof by example, but you'll see how it generalizes very easily. So want to show, for example, that 7 to the 8th power is 1 in U15 without computing 7 to the 8th power. Like, I just want to give some sort of argument that says that this actually does work. Because if it's going to be a proof that generalizes, I can't just compute it and show you that it equals 1. I have to give you some argument. So here's the thing. U15, as we said, as a set, well, it's everything less than 15 that doesn't have a 3 or a 5 in it, right? So 1, 2, 4, 6 has a 3, 7, 8, no 9, no 10, 11, no 12, 13, and 14, right? So it's these 8 elements. Here's what I want to do. I want to multiply everything by 7. Because 7 is what I'm trying to show here. So, like, let's multiply everything by 7. Oh, jeez. Okay, so we get the set. Well, I'll write it kind of the dumb way first. 7 times 1, 7 times 2, 7 times 4, 7 times 7, 7 times 8, 7 times 11, 7 times 13, 7 times 14, right? Let's actually compute this. So 7 times 1 is 7, 7 times 2 is 14. 7 times 4 is 28. Mod 15, that's 13. Right? So I'm just computing each of these. Mod 15. 7 times 7 is 49, which is 4, because it's 4 more than 45. Okay. 56 is 11. 77 is 2. 77 is 2 more than 75. 91 is 1. 7 times 13 is 91. And 98 is 8. Right? If I just compute all these and reduce them mod, reduce them mod 15, then these are the numbers we get. And look, this is actually exactly U15 again. It actually, well, you can prove that basically this is a map. It's a map from U15 to itself. We know that the units are closed under multiplication. If we multiply 2 units, we get another unit, right? Like 2 times 4 is 8. 4 times 7 is 28, which is 13, and so on. So we know it's closed, and it turns out that if you multiply everything by a fixed number, so you get a map from U15 to itself, and this kind of shows you that the map's actually a bijection. So i.e., the map from U15 to U15, where x gets mapped to 7x, is a bijection. You can prove this in general, that if you multiply by a fixed unit, you just sort of permute the units. Right, and so particular here, we get this set back. But that means that this set equals this set, right? And if you think about that, if 2 sets are equal, well, here's the kind of the funky idea. If 2 sets are equal, then the product of the elements, so I'll just write this in general. If S1 equals S2, those are supposed to be sets. Maybe I'll use S and T. If S equals T sets, then the product of the elements of S equals the product of the elements of T. It's a fancy way of saying if I multiply everything together in S, it should be the same thing as if I multiply everything together in T. It seems like almost a dumb thing to say. Product of the elements of S equals really got to work on my iPad handwriting, you guys. Equals the product of the elements of T. So here, in this case, if I just focus on these two sets, this says that, in fact, so 7 times 1 times 7 times 2 times 7 times 4 times 7 times 7. Hopefully you see where I'm going with this. Times 7 times 8 times 7 times 11 times 7 times 13. This is just at the edge of what I would want to write out fully. Well, that is going to equal just 1 times 2 times 4 times 7 times 8 times 11 times 13 times 14 in U15, right? Those are equal to each other, but we can rearrange this one, right? If we rearrange, right, we can pull all the 7s out. And so it's really 7, you know, it's 7 times 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 7. Ah, that's 7 to the 8th. So 7 to the 8th times 1 times 2 times 4 times 7 times 8 times 11 times 13 times 14 equals 1 times 2 times 4 times 7 times 8 times 11 times 13 times 14. And there you go. Because we're in a group, we can actually cancel. So we cancel both sides. We cancel this product from both sides. And therefore, 7 to the 8th power is 1 in U15. So we did it without actually computing anything directly. I guess we computed, I mean, I guess I computed these numbers up here. But the point of all this was just that you get the same setback, which is the idea that this is a bijection. And so honestly, just to make this video not be insanely long, I'll just say, like, basically to write the real proof, just turn the numbers into letters. I guess you have to prove that that map's a bijection. The map mentioned above is a bijection. But that's, it's basically what we're like. It's basically the same proof. You would just have to, that's real proof, not red proof. You would just have to, like, use letters. Like for 7, use the letter A. For 8, use phi of M. And then you just give these, the numbers 1, 2, 4, 7, 8, 11, 13, 14. You would give them just, U1, comma, U2, comma, whatever. You just label everything with letters, write it all out, and you get the exact same proof. So I'm not going to actually write down the proof, the formal proof, but because the idea is what matters. And this is a cool idea. And it didn't matter. It just mattered that we were, really, it just mattered, 7 was just chosen as an element of U15, and 8th power was the number of elements in U15. So that would work for any mod, for any element. Same proof would work. Okay. Feels a little slapdash, but I'm going to stop there.